Okay, now we move on to chapter 4, physical transformations of pure substances. So from chapter 4 we are going to deal with changes, and we'll first consider physical changes. There are two different kinds of changes: physical changes and chemical changes. Chemical changes refer to chemical reactions, which is much more complicated than physical changes, right? We'll consider chemical reactions in the following chapters. Okay? First, we'll deal with simpler system. Physical changes, such as transition, phase transition, melting, boiling, freezing, something like that. Okay? So, we'll basically deal with different phases, such as solid, liquid, and gas. Okay? So we'll first consider those different phases, how those different phases are represented in a simple diagram called phase diagram. Okay? So we'll consider related properties such as stabilities of phases, phase boundaries, typical phase diagrams, three representative phase diagrams. Okay? And we'll also deal with phase stability. Which phase? There are basically three representative phases, right? Solid, liquid, and gas. Which phase is the most stable one at a given pressure and temperature? And that answer is given based on our knowledge in thermodynamics from chapter 1 to chapter 3. Okay? Based on those knowledges, we can determine which phase is the most stable one. And also we'll consider phase transition, physical change from one phase to another. Okay? And finally we'll classify several different phase transitions into a certain kinds. Okay? So this phase transformation is the simplest application of thermodynamics to chemistry. Okay. So up to here, up to chapter 3, we learned about many different concepts in thermodynamics, right? Many different formula, many different variables, etc. Their relations, right? From chapter 4, we'll do real applications, and the simple one, right? So we'll apply the laws of thermodynamics to physical transformations of pure substances. That's the most simple application of thermodynamics. Okay? So the question in this chapter is, how do we determine the most stable phase of a substance at a given pressure and temperature? Okay? That's a very important question in this chapter. And the answer is very simple. The Gibbs energy can give us the answer to this question. We learned that when we dealt with the second law of thermodynamics, okay, we learned that spontaneous processes, spontaneous changes, have negative change in Gibbs free energy, right? Spontaneous or irreversible changes always accompany negative change, decrease in Gibbs free energy, right? So, if you want to answer to this question, all you need to do is compare the Gibbs free energy of a certain substance for different phases. Okay? You determine the Gibbs energy of a certain substance as solid, also as liquid, and as gas. Okay? You compare those three numbers, three Gibbs free energy. And the phase with the lowest Gibbs energy is the most stable one, because spontaneous changes accompany negative change in Gibbs free energy. Okay? So you can simply calculate Gibbs energy for different phases and compare them and pick the lowest one. That's the most stable one. Okay? And especially for pure substances, if you recall from chapter 3, for pure substances, chemical potentials are same as molar Gibbs energy, right? So basically, phases with the lowest chemical potential is the most stable one. So we got the answer. There was an important question, and we got the answer. Simply compare chemical potential for different phases, and phase with the lowest chemical potential is the most stable one. Alright, so before we move on, let's introduce a few important concepts, a few important terms. First, phase. Phase is defined as a form of matter that is uniform throughout in both chemical composition and physical state. So phase is something like a certain state of matter that should be uniform in terms of chemical composition and physical state. So as you all know, there are solid, liquid, and gas, right? So those phases, solid, liquid, or gas, have one phase, right? So to represent the number of phases present in a system, we denote the number of phases, okay, in a system as P, large capital P. So for example, solid, liquid, or gas state has P of 1, right? Only one stable phase, right? How about mixture of gases? For example, air. Air is composed of nitrogen, oxygen, argon, CO2, etc., right? How about mixture of gases? Does it have one phase or two phases or more? Gases mixture have one phase. P is equal to 1. The reason why is that mixture of gases are uniform in terms of chemical composition and physical state, right? Air is uniform in terms of chemical composition and physical state. That's why P is equal to 1 for gas mixture. Similarly, for example, solution like salt solution. If you dissolve NaCl in water, okay, NaCl dissolved water, that also has one phase. P is equal to 1 because they are uniform in terms of chemical composition and physical state. How about ice in water? If you have water, a cup of water, and you put some ice in it, then they have two different phases, right? Ice and water, right? In that case, P is equal to 2, right? So you have to differentiate between the one phase and two different phases. The second term is phase transition. It's simply change of physical state of a pure substance, right? Phase transition is defined as spontaneous conversion of one phase into another at a specific temperature and pressure. The importance is here spontaneous conversion. That change, that transition should occur spontaneously, irreversibly. Okay? So that's the definition of phase and phase transition. Alright. So, from previous slide, to determine the most stable phase at a given pressure and temperature, we needed to compare chemical potential, right? And chemical potential is basically molar Gibbs energy, okay, of a pure substance. Okay. So, if you recall the molar Gibbs energy from chapter 3, okay, if you remember, mu is basically molar Gibbs energy. And remember how mu or Gibbs energy changes as a function of temperature. You remember? That was same as minus entropy, molar entropy, right? So you might remember this kind of diagram. T Gibbs energy changes like this for gas, liquid, solid, something like that. Okay? Okay? Right? So if you plot the same diagram for chemical potential as a function of temperature, you will get this, right? Sorry. You get basically this kind of diagram, right? Same. Okay? Chemical potential as a function of temperature, they decrease, right? Because partial derivative of chemical potential as a function of temperature is minus molar entropy. Okay? And gas has the largest slope, gas, followed by liquid and solid, right? Gas has the largest slope, followed by liquid and solid, right? Okay? And let's compare chemical potential of solid, liquid, and gas. Let's compare them at a given temperature. For example, in this region, at low temperature, chemical potential of solid is here, chemical potential of liquid is here, chemical potential of gas is somewhere here, right? Solid has the lowest chemical potential when temperature is low. Okay? So, at low temperature, solid is the most stable phase. Right? How about here, in the middle? Chemical potential of liquid here, chemical potential of solid here, gas here. Right? So, liquid has the lowest chemical potential. That's why here, liquid is the most stable phase. Similarly, at high temperature, gas is the most stable phase. Okay? And, as you can see, there is a certain temperature at which chemical potential of two different phases meet together, right? For example, here, at this temperature, chemical potential of solid and liquid meets. And this temperature is temperature at which phase transition between solid and liquid occur, which is melting temperature, right? Melting temperature TF. Okay, and this temperature here, chemical potential of liquid and chemical potential of gas meets together. They are same here. And this temperature is at which phase transition between liquid and gas occurs, and that's boiling point, or TB, right? Very simple, right? Simply, based on thermodynamic knowledge that we have learned in chapter 3, we can determine which phase is the most stable one as a function of temperature. Right, so phase transition. So, based on thermodynamic knowledge, we can determine which phase is more stable, which transition is spontaneous, right? But that does not tell us anything about the rate of transition, how fast that spontaneous process occurs. It does not tell us anything about rate. Okay? So, thermodynamically, a certain phase might be more, not might be, a certain phase is more stable or more unstable, right? But kinetically, in terms of rate of transition, that process, that spontaneous process might be very slow. For example, the representative example, is the case of diamond and graphite. Diamond and graphite has same chemical formula, just carbon, right? So if you compare the chemical potential of diamond and chemical potential of graphite at for example, at 1 bar 25 degrees C, chemical potential of graphite is actually lower than chemical potential of diamond. So this is the more stable phase. All carbon material should exist as graphite. So change from diamond to graphite to the right is a spontaneous process. Okay? But that process is very slow. It takes thousands, tens of thousands of years to spontaneously convert diamond to graphite, because it involves basically exchange of atomic positions. Okay? So although graphite is more stable thermodynamically, okay, or in other words, diamond is thermodynamically unstable, but they exist, right, as diamond ring, because this spontaneous process is really slow. Okay? So this kind of phase, which is thermodynamically unstable but persists due to kinetic hindrance, is called metastable phase. Okay? This kind of phase is called metastable phase. Alright. So same again, you can just read the phase stability and phase transitions. Okay. It's very simple but very important. Thermodynamic criterion of equilibrium. When you deal with phase transition, we'll encounter equilibrium, right? Because we are basically dealing with 2 different or 3 different phases at equilibrium when phase transition occur. Okay? So, at equilibrium, the chemical potential of a substance is the same throughout a sample, regardless how many phases are present. That's obvious, right? At equilibrium, for example, when phase transition occurs, when melting occurs, or when boiling occurs, we know that 2 different phases have same chemical potential. 2 different phases have same chemical potential. That's just given in this statement, right? At equilibrium, chemical potential is same. That's all. Okay? Very simple but very important. Using this simple statement, we'll deal with many different problems in the following sections. Okay? Alright, let's move on. Phase boundaries. In previous section, we saw that the most stable phase at a given temperature and pressure is determined by simply comparing chemical potential, right? So we can do it for many different pressure and temperature, and we determine the most stable phase of a certain pure substance, and we draw it in a certain diagram that is called phase diagram. Okay, so phase diagram basically shows regions of pressure and temperature where phases are thermodynamically stable. Okay, so here shows phase diagram, a simple one. Y-axis is pressure, x-axis is temperature. Okay, so for example, here at this pressure, at this temperature, the most stable phase is solid. Okay, here, this pressure, this temperature here, the most stable phase is liquid. Basically, this simple diagram shows which region, at which region the most stable phases are. Solid here in this region, liquid in this region, vapor in this region. Very simple. Okay? So there are three different regions at which certain phases are most stable. And there are also boundaries, these green lines, right? Separating these different phases, right? First, here, this phase boundary basically separates solid and liquid. Okay. So, from this phase boundary, we can determine the melting point. How? Because at a certain pressure, that pressure meets, let's just use the whiteboard. All right. All right. From the phase diagram, like this, temperature, pressure, something like this. Okay. From solid liquid phase boundary, for example, at this pressure, it meets with here. Okay. So this basically this boundary represent a region, a pressure and temperature at which solid and liquid are in equilibrium, because on this line they coexist, right, together. Okay, so they are phase boundary. So at this pressure, the temperature basically represents the temperature at which these two phases are at equilibrium. That means melting temperature. Right? Simple, right? Similarly, how about liquid vapor boundary? Here, this line. Liquid and vapor. For example, at a certain pressure, this boundary basically represents the pressure or temperature at which liquid and vapor coexist at equilibrium. Okay? So, at this pressure, this temperature represents the temperature at which these two phases are in equilibrium, which means this temperature is boiling temperature. Okay? Or, in another way, at a certain temperature on this line, on this boundary, liquid and gas coexist, and that gas material would have a vapor pressure, right? Okay. So at this temperature, this pressure basically represents vapor pressure of the gas. Okay. You can have many different information from this simple phase diagram. Okay. Right, what else? We have here another point called critical point. You might remember from previous chapter that when we dealt with condensation of carbon dioxide, okay, CO2, we encountered critical point or critical temperature, right? That's it, that's this one. So at the temperature or pressure at this point is called critical temperature, critical pressure, or critical volume, something like that. Okay. All right. And we have also this point here, which is called triple point. And at triple point, solid, liquid, and gas, three of them coexist, right? All of them are at equilibrium, okay? At triple point. move on. So we dealt with phase diagram and what phase boundaries are, what kind of information we can get from this simple phase diagram. Alright. Critical points and boiling points, we already have seen it, right? To compare boiling points and critical points, you can simply compare the boiling, heating of the liquid in an open vessel and closed vessel. For example, in an open vessel, if you heat a liquid sample, as we heat more and more, the temperature will rise, right? And when the vapor pressure of that material is equal to the external pressure or atmospheric pressure, then the material starts to boil, right? Okay. The temperature at which the material starts to boil is called boiling temperature, right? Okay. How about if you heat the sample in a closed vessel? Basically, we have closed sample and we put some liquid in it and we just heat it up. And temperature will rise, and as the temperature rises, the vapor pressure of the material increases also, right? And after a certain point, after a certain temperature, the boundary between liquid and gas disappears, and the material becomes something in between liquid and gas. There's no boundary. That point is called critical point. Here. From here, we just heat the sample again and again, and it just follows the line. And after this point, there's no more liquid vapor boundary, and the physical state of this material is something in between liquid and gas, right? Okay. So at that point, the point is critical point, and we can determine the critical temperature, pressure, and volume. Okay, and the physical state above this critical point, like in this region, is called supercritical fluid. Okay, so supercritical fluid has very interesting physical properties because it has both liquid-like or gas-like properties. Okay. All right, we already have considered this from phase diagram. Okay, the phase rule. Out of nowhere, there is a phase rule like this. Actually, this phase rule was deduced by Gibbs. Gibbs again, Gibbs free energy, right? That Gibbs was a genius, so he also studied about this phase. So phase rule is given here, very simple equation, right? F is equal to C minus P plus 2. So what each of these variables represent is, first, F is called variance or degree of freedom. So basically F represents the number of intensive variables that can be changed independently. Okay, very difficult, right? You remember what intensive and extensive variables are, right? From chapter 1. So F basically represents how many intensive variables we can change independently, okay? Alright. So here, intensive properties, as represented in F, include temperature, pressure, and composition. Okay? Temperature, pressure, composition. So among temperature, pressure, and composition, how many variables we can change independently? That's F, or variance. Okay? And here C is number of components. How many components are present in a system? Okay? And P is number of phases at equilibrium. We already have introduced P, right? So F is equal to C minus P plus 2. Very simple equation, but we need to derive it. Okay? So, first, single component, single phase system. Let's consider a very simple one, simple system. Okay? We only have a single component, one phase. Okay? If C is 1 and P is 1, then F is 2. Okay? Which means that we can just use the phase diagram. So here, for a single component, phase diagram looks like this, for example. Okay? If there is only one phase present, step 1, that means that it is somewhere like here, or here, or here, something like that, right? Then, for example, let's say that we are here. And since it is single component, we don't really need to worry about composition, right? Only intensive variables we can change is temperature and pressure, right? So, from here, can you change the pressure? Like here? Like this? Right? Okay? That's possible. How about temperature? Can you change it? We can change it. We can increase temperature, decrease the temperature, increase the pressure, decrease the pressure. Those are possible, right? So, we can independently change both temperature and pressure. Okay? That's why F is 2. Temperature and pressure. Okay? How about single component, 2 phases in equilibrium? One component, so we don't need to worry about composition, but 2 phases are at equilibrium. So C is 1, but P is 2. So the resulting F variance is 1. Why? Single component, phases are at equilibrium. So for example, they are on this boundary, right? And they should maintain equilibrium, solid and liquid, for example. On this line, can we change both temperature and pressure independently? That's not possible, right? If you try to increase the temperature without moving out of this line, if you try to increase the temperature, it automatically increases the pressure, right? Following this line, right? You cannot move from this line. So if you determine either pressure or temperature, the other variable is automatically determined. That's why the variance is 1. Okay? So, although we only consider very simple cases, we can generalize it, okay, to derive the phase rule. Okay. So, for one component system with 2 phases in equilibrium, which means that since 2 phases are at equilibrium, if you recall, chemical potential at one phase, alpha phase, is same as chemical potential of second phase, beta phase, right? Okay. So we have one equation. And we have 2 different intensive variables, pressure and temperature. Okay. Although we have 2 variables, we only have one equation. Then variance is 1, because if you have a certain number for pressure, temperature will be determined automatically, right? Okay. How about one component system with 3 phases at equilibrium? Alpha phase, beta phase, and gamma phase. They are at equilibrium, which means that there are these equations. Chemical potential of each phase are same, right? Basically, we have 2 equations, this equation and this equation. Right? We have 2 variables, pressure and temperature. We have two equations that automatically determines pressure and temperature. There is no option. There is no independent choice. So variance is 0. Okay? Now, let's generalize the case. This is very simple because we only considered one component system. Okay? So let's generalize it. Let's consider that we have C component system with P phases in equilibrium. Okay? First, let's calculate how many intensive variables are present. First, as I mentioned, intensive variables include temperature, pressure, and composition. Okay? So we have temperature and pressure, we have two intensive variables first. How about composition? Okay. For composition, let's say that we have C number of components. Then we'll have this relation, right? From mole fraction, x1, x2 plus xc should be equal 1. Which means that if you have information about x1, x2, blah blah blah, xc minus 1, then the last one, xc, is automatically determined, right? So the degree of freedom is c minus 1, right? C minus 1. Okay? And for each component, we have p number of phases, so we need to multiply p. Okay? So this is number of intensive variables for composition, and we have two more, pressure and temperature. Okay? Alright. So since p different phases are at equilibrium, okay, which means that we have this kind of equations for p number of phases, right? Chemical potential of alpha phase, chemical potential of beta phase, chemical potential gamma, blah 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 blah. P phases are same, right? Okay? Which means that basically we have p minus 1 equations, right? When we had 3 different phases in equilibrium, we had 1 and 2 equations, right? When we have p phases, we have 1, 2, 3, 4, p minus 1 equations basically, right? Okay? So we need to subtract this number, p minus 1, right? And we have these equations for each component, so we need to multiply by c. Okay? So if you calculate this, we finally get F is equal to c minus p plus 2. Okay? Simply we got phase rule. Alright. So here shows basically the phase rule, phase diagram. You can look it up. Alright. So different materials have different form of phase diagrams. So here shows 3 representative phase diagrams. The first one is the most common one, is CO2. So it looks like this, as we saw in previous section, right? Phase boundaries, solid, liquid, and gas, right? So as you see, we have positive slope of solid liquid boundary, okay, which means that as we increase the pressure, melting point also increases. Okay. For CO2, triple point is here at 5.11 atm and 216.8 Kelvin. So triple point lies above 1 atm. Okay. So at normal pressure, at 1 atm, solid and vapor phases are at equilibrium, depending on the temperature. Right? That's why we can easily see dry ice, solid state CO2. Okay. Another important characteristics of phase diagram of CO2 is critical point here. Critical point lies at 72.9 atm, 304 Kelvin. It's relatively low temperature. Okay? So it's relatively easy to make supercritical CO2 compared to other materials. Okay? So for supercritical fluid, CO2 is the most used material. Okay? And as I mentioned, supercritical fluid has very interesting properties because they are in between liquid and gas. So they are used in many different applications. Especially supercritical fluid has good properties of dissolving material, has very good solubility. So they are used for many different types of extraction, decaffeining of coffee or extraction of oils, etc. Okay. Next representative diagram is for water. Okay. It's a little more complicated than CO2, right? Solid, liquid, and vapor, but there are many different types of solid area. Okay. The main difference between CO2 and water is that the slope, solid liquid slope here, is negative for water. Okay, which means that as you increase the temperature, pressure, melting point decreases, and that might explain glacial motion. If you watch the documentary of Antarctica, something like that, you see very large glacier moves, right? It's very unlikely that heavy glacier moves, right? That might be due to this phase diagram, because as we increase the pressure, since glacier is very heavy, the pressure at the bottom of that would be really huge, right? The melting temperature decreases, okay? Which means that at the bottom of the glacier, okay, it would melt relatively easily compared to on top of that. So that might explain how this huge, heavy one moves. Okay? And at very high pressure, there are many different phases of ice, because at high pressure, those pressure could induce different structures of molecules. Okay. Third one is for helium, especially at low temperature. As you see this diagram, it is at 0, 1, 2, 3, 4 Kelvin, really low temperature. So as you see, there is solid, liquid 1, liquid 2, gas. Right? And liquid 1 is just liquid, liquid 2 is superfluid. It's not same as supercritical fluid actually, so it's called superfluid. Okay? So as you see, there is no phase boundary between solid and gas, right? Because helium atoms are really light, right? So it's not really just with small energy, it can just totally take apart these helium atoms. And there is liquid and superfluid. Superfluid is some fluid. It has very interesting property, such as they flows without any viscosity. Every liquid has viscosity, right? But this superfluid does not have viscosity, so it has very interesting phenomena. And that's pretty much it. Not really common one. Okay. Okay, let's move on. From previous sections, we have learned that in equilibrium, chemical potentials of each phase are same, right? At equilibrium, chemical potentials are same between two different phases or three different phases. Okay? From this section, we'll deal with how phase equilibrium vary as the conditions such as pressure and temperature change. Temperatures are changed. Okay? So basically, we'll see if temperature or pressure changes, the equilibrium changes. How equilibrium changes. Okay? So first, let's consider temperature dependence of phase stability. Okay? So, we have learned from previous section that chemical potential change as a function of temperature at constant pressure corresponds to minus molar entropy, right? So, since entropy is positive, okay, minus entropy is negative, which means that as temperature increases, chemical potential decreases. As temperature increases, chemical potential decreases, right? And we already have seen this diagram in previous section, right? As shown here, right? As temperature increases, chemical potential decreases, right? For each phase, solid, liquid, and gas, right? Okay. So as we just saw in previous slide, that for solids and liquids, the slope of chemical potential fall is not as big as the slope of gas, right? Okay. This part, the temperature dependence of phase stabilities already have covered in previous sections. Now let's consider the change of equilibrium upon changed pressure. Okay? First, we'll consider melting response to applied pressure. If you apply pressure, would melting point change? Would melting point increase or decrease or remain the same? Okay? Let's first consider how chemical potential changes as a function of pressure. So at constant temperature, chemical potential change, the chemical potential change as a function of pressure corresponds to molar volume, right? Okay? And molar volume is positive volume, so which means that chemical potential increases as pressure increases. Okay? Right. Then let's consider the chemical potential change between two different phases of solid and liquid for a certain material. Okay. First, from this diagram on the left, the black lines represent the chemical potential change of a certain material, chemical potential of solid, chemical potential of liquid. Okay? If pressure increases, if applied pressure increases, okay? If pressure increases, chemical potential increases, right? So, if pressure increases, chemical potential would increase upward, right? How much? This much. Okay? Molar volume. So, if molar volume of solid is smaller than molar volume of liquid, which means that the increase in chemical potential upon applied pressure, for solid it increases a little bit, small amount, right, from this black lines to green lines, right? For liquid, since the molar volume of liquid is larger than this one, the increase is larger than increase in solid, right? So we got these green, blue lines, right? And if you recall, the intersection at which chemical potential of solid and chemical potential of liquid meets corresponds to melting point, right? And when we apply pressure, since chemical potential increases from here to here, from here to here, okay, melting point moves from here to here, right? Melting point increased, okay? When molar volume of liquid is larger than molar volume of solid, melting point increases as we increase the pressure, okay? This is the most cases. For most materials, molar volume of liquid is larger than molar volume of solid. Okay. On the other hand, if molar volume of solid is larger than molar volume of liquid, then by increasing the pressure, the increase in chemical potential for solid would be larger from here to here than liquid, right? From here to here. So in this case, melting point decreases to the left, right? Okay? So if this is the case, if we increase the pressure, melting point decreases. This is the case for water, right? For H2O, molar volume of ice is larger than molar volume of water, liquid, okay? Alright, so as a conclusion, if you apply pressure, melting point changes. And if, depending on the molar volume of solid and liquid, it could either decrease or increase or decrease. So here's an example, so you can calculate how much chemical potential changes upon applied pressure. Just do it yourself. Alright. So in previous slide, we considered how melting, basically solid liquid boundary changes upon applied pressure. How about liquid vapor boundary? If you apply pressure, would liquid vapor boundary change? Okay. Especially, would vapor pressure change? Okay. So let's assume that we apply pressure to condensed phase, to liquid. Then the result is the vapor pressure increases. Okay. Let's just imagine this kind of experiment. So we basically have liquid here, and we apply pressure by pushing liquid from top to the bottom using this kind of, what is it called? Some kind of sponge. This sponge has the properties of, they are permeable to vapor but not liquid. They can push liquid, and by pushing it, the vapor can penetrate through this spongy. So since we apply pressure to the bottom, right, to the liquid, more liquid would vaporize through this sponge and vapor pressure would increase, right? We can imagine it, right? Or similarly, we can exert pressure on this liquid by using inert pressurizing gas, right? Some inert gas, such as helium, neon, something like that, okay? To simply increase the pressure to exert on this liquid. So either way, either mechanically pushing or using pressurizing inert gas, you can push the liquid, and that will result in increase in vapor pressure. That's obvious, right? Because we push the liquid, we squeeze it, right? Then, how much vapor pressure increases? We want to know, especially how much. Quantitatively, we want to know how much vapor pressure increases as a result of this increase in applied pressure on the liquid. Okay? The result is that, like here, this equation. This is the vapor pressure after we apply pressure. This is P star is vapor pressure without any additional pressure, and the final pressure increases this much, epsilon over Vm delta P over RT. Here Vm is molar volume of liquid, okay? Delta P is applied pressure to the liquid by either using mechanical squeeze like piston or pressurizing inert gas. Okay, so if you apply a certain pressure, you increase the vapor pressure of the gas this much. Okay, why? Let's derive it. Okay, let's use the whiteboard. Okay, so we want to show that P is P star epsilon over Vm L delta P over R T. Okay, the derivation is simple. We'll only use one simple statement, which is that at equilibrium, chemical potentials of 2 or 3 different phases, just chemical potentials of different phases, are same. So at equilibrium, here, at equilibrium, liquid and gas, okay, chemical potential of liquid and vapor will be same, right? Chemical potential of liquid and chemical potential of gas will be same. Okay? So let's say that we apply pressure. And after we apply pressure, liquid and gas, as a result, would be in equilibrium, right? Which means that chemical potential of liquid would change, but, right? Also, chemical potential of gas would change after we apply pressure. And that change would be same, right? Because after apply pressure, liquid and gas would be in equilibrium. Okay? Then how much chemical potential changes for liquid? How much chemical potential changes for gas? Okay? First, for liquid. Since we applied pressure P, to the liquid, okay? You remember how much chemical potential changes as a function of pressure, right? That corresponds to molar volume, dP, okay? If you have noticed, the applied pressure to the liquid is denoted as large capital P, and vapor pressure is small letter, right? Okay. So you have to differentiate between them. So chemical potential change for the liquid corresponds to VML, the large capital P, okay? Similarly, chemical potential change for gas would be same as Vm G B P here, right? Here, small letter P, right? Gas pressure, okay? All right. If the gas is a perfect gas, then molar volume will be same as RT over P. Okay? So these two should be same, right? Okay? So let's just write it down. Vm LdP is equal to RT over P dP. Okay? Let's integrate, right? Let's integrate. Okay? Initial pressure for gas, basically vapor pressure, before we apply pressure to the liquid would be P star, right? And the final pressure after we apply pressure to the liquid would be P, vapor pressure. Okay? How about for liquid? Initial pressure that is applied to the liquid initially would be same as P star, right? That's the only pressure applied to the liquid before we apply additional pressure, right? And after we apply additional pressure, the resulting pressure exerted on the liquid would be P, vapor pressure of the gas, plus delta P, right? See it? Okay. So for gas, initial pressure is P star, vapor pressure for pure substance. And the final pressure is P, vapor pressure. Pressure for the liquid, initial pressure is P star. Only exerted pressure on the liquid would be P star, right? And the final pressure will be P plus P star. Here at delta P is the applied pressure on the liquid. Okay? Alright. Here, we'll actually, as a result, we'll see it later. But anyhow, we just assume that this P and P star are very close to each other. Although by applying pressure on the liquid, we increase the vapor pressure, and that increase is very small. So we can assume that this P is very close to P star. Okay? You can simply assume it. Alright? And let's do the integration. Okay? Here, simple, right? Molar volume of liquid is basically constant. And we get delta P. Right? Here, RT is basically constant. Right? Log P star P. Okay? If you express it as a function of basically P, you can get P star, where is it? Epsilon Vm L delta P RT, the result here, right? Okay. Simply we derive this relation. Okay. Let's go back. Alright. To derive this vapor pressure change upon applied additional pressure on the liquid, we assume that the increase in vapor pressure is very small, right? We need to demonstrate it. Okay? So, we got this relation here. right? And epsilon something, right? Ex can be described as Taylor series, right? Infinite series. If x is very small. Okay? So let's assume that x is very small. So this part is very small. Okay? We assume it. Then P star would be approximately, this Ex would be approximately 1 plus x, right? 1 plus x. So we just simply calculate it using a simple example for water. Density is like about 25 degrees C, molar volume is 18.1 cubic centimeter per mole. We put the numbers in, and the increase in vapor pressure corresponds to only 0.73%, even less than 1%. So our initial assumption is valid, right? We assume that the increase in vapor pressure is very small, right? So that was a valid assumption. Okay? All right. Occasional phase boundaries. Okay. We have seen a representative phase diagram before, right? And how can we draw that kind of diagram? Would it be very difficult, or would it be easy? So, for example, there is phase boundary between two different phases. How can we draw this line separating two different phases? Okay? If we can draw this line, especially like 3 or more lines between two different phases, then we can make the phase diagram, right? And this line, phase boundary, basically represents at which chemical potential of two different phases, alpha phase and beta phases, are same, right? So based on this simple equation, chemical potential is same. We might be able to draw these lines of phase boundaries. Okay? So let's do it. Let's just draw the phase diagram for a certain material. Okay? So to do that, all we need to know, as you see from this phase diagram, all you need to know for this phase boundary is the relation between pressure and temperature. If you have an answer for the relation between pressure and temperature, then you can have this boundary, this line, right? So you need to find a relation between pressure and temperature, how pressure changes as a function of temperature using this simple equation. Okay? So let's do it. So let's say that two phases stay in equilibrium with one another. Okay? Then chemical potential will be same, right? Even if there is a certain change, okay, the change in chemical potential will be same, right? So d mu alpha should be equal to d mu beta between two different phases of alpha and beta. Okay? And d mu can be represented as minus Sm dt plus Vm dp. Okay, we already have seen it, right? Chemical potential change as a function of temperature corresponds to minus S minus molar entropy. Chemical potential change as a function of pressure corresponds to molar volume. Okay? Since chemical potential change for two different phases are same, this should be same as this. Okay? If you rearrange these terms as a function of dp and dt, you get dp dt. How pressure changes as a function of temperature, their relations between each other. Okay, that corresponds to delta S transition, delta V transition. If we have an information about entropy change upon phase transition between two different phases, and also volume change upon this physical transition between two different phases, then we can determine how pressure changes as a function of temperature. Okay? These are all you need to know. If you have information about this, you can determine this, and you can draw a phase boundary, and finally you can make phase diagram. Okay? So this equation is called Clapeyron equation. Okay? Alright. So let's draw it. Okay, let's use the whiteboard again. Let's draw the phase boundary and phase diagram. Alright. So you start from Clapeyron equation. dPdt is equal to delta transition S over delta transition V. Okay. You start from here. Let's draw each phase boundary. First, let's draw solid liquid boundary. Solid liquid boundary. When physical transition or physical such as melting or vaporization occur, entropy change corresponds to, remember, T over delta H, right? Remember? When physical change, phase transition occurs, temperature is constant, okay? And phase transition occur is basically at constant pressure, basically in equilibrium. So delta S is same as T, delta H over T. Okay, so we get transition V. Okay, so if you have an information about entropy change, melting temperature, volume change, then you can determine boundary between two different phases. Okay? How about solid liquid boundary? So now we have dP dt is equal to delta fusion H over T delta fusion V. Okay? If melting occurs, enthalpy change is positive, temperature is positive, volume change is positive, right? Most cases, right? So you can first know that this is positive. Oh, pressure increases if temperature increases. Okay? For phase boundary, the slope of phase boundary between solid and liquid for most materials are positive. Okay? So let's get the exact relation between pressure and temperature or solid liquid boundary. Okay? You can do the integration, right? dP dt is equal to delta H over T delta V. So let's move dt to the right side. Okay? And let's do the integration. Let's say that initial pressure and temperature corresponds to T star and P star. And the final temperature as temperature and pressure changes corresponds to P and T. And let's do the derivation. So we have P minus P star on the left side, which should be same as delta H and delta V upon phase transition is constant basically, right? So delta fusion H over delta fusion V. All you need to do is integrate 1 over T, which corresponds to log T over T star. Okay? If T and T star are very close to each other, okay? Just assume it. If T and T star are very close to each other, log T over T star can be approximately same as, you can rearrange it as log 1 over T star T minus T star, not approximate here. This is approximately T minus T star over T star. Okay? You might recall it from mathematics class. Okay? Log 1 plus x is approximately same as x when x is very small. Okay? So if you put this expression to here, what you get is P is equal to P star plus T minus T star over delta fusion V delta fusion H. Okay. Pressure as a function of temperature. Okay, which is just pressure as a function of temperature, which is just a simple straight line. Okay? So, solid-liquid boundary corresponds to simple straight line. So we got one phase boundary. Solid-liquid boundary looks like this. Okay? Very simple, right? Okay. You can do the same thing for other boundaries. Let's do it for other boundaries. First, liquid vapor boundary. So we now got solid liquid boundary like this. Okay? Now let's move on to liquid vapor boundary. Liquid vapor boundary. Pretty much same. dp dt will be corresponds to delta H vaporization instead of fusion, right? Vaporization volume, right? Everything is same, right? So delta H for vaporization is positive, positive, positive. So it's also positive. Oh, so liquid vapor boundary also have positive slope. Okay, we can conclude it. Okay. But the thing is, if you compare this value with fusion, compare these two, okay? Volume change for melting, for vaporization. Volume change for melting, vaporization is, if you compare these two, much larger, right? If you melt solid, if you melts basically to liquid, volume increases a little bit. But if liquid vaporized to gas, volume change is huge, right? This is much larger than this, which means that this value basically corresponds to slope of liquid vapor boundary is not large as slope of solid liquid boundary, right? Which means that liquid vapor boundary has much smaller slope, something like this. We don't know the shape of the boundary, if it is linear or curve or whatever. But anyhow, the slope is smaller than solid liquid boundary. Okay. So let's calculate it. So we got this, and if the vapor, the volume change from liquid to gas, basically, sorry, the volume change from liquid to gas would be pretty much same as volume of gas, right? Because volume of liquid is much smaller than volume of gas. Okay, and if you assume that the gas is a perfect gas, then molar volume would be same as RT over P using ideal gas law. Okay, so if you rearrange it, you get, where is it? You have P here, so P, so dP is equal to RT square delta H dt. Okay, a little bit more complicated than before, right? It's not easy to do this integration by yourself, so let's look at the result. If you solve it, you get this expression. Okay. Here the chi corresponds to very complicated, right? So let's use just use the result. And if you plot P as a function of temperature, the result, the liquid vapor boundary, looks like this. Okay, not straight line, but like curved. Okay. All right. So we got 2. Finally, how about solid vapor boundary? Everything same, right? For solid gas boundary, you got same expression, but only difference is it is for sublimation, not vaporization, sublimation. Right? Okay. For sublimation, volume change from solid to gas, liquid to gas. These two would be pretty much same, right? These two would be pretty much same, right? Volume change from solid to gas or volume change from liquid to gas. But enthalpy change for vaporization and for sublimation, if you compare these two, this will be a little bit larger, right? For sublimation. So which means that to solve this, if you solve this equation, differential equation, you'll get pretty much same form, right, of equation, but slope is a little bit larger than this. Okay, so the shape is pretty much same, but the slope is larger than this. So like this. Okay. Okay. So you finally got the phase diagram by simply getting information about each of these phase boundary between solid and liquid, liquid and vapor, and solid and vapor. Okay? You can simply draw a phase diagram by drawing three different phase boundaries. Okay. Alright, let's move on to the final section of this chapter. Fast classification of phase transitions. We have encountered only a few different kinds of phase transitions, such as melting, vaporization, sublimation, etc. But there are many different kinds of phase transition, including solid-solid liquid phase transition, conducting, superconducting phase transition, fluid, superfluid phase transition, etc. Okay? So, people needed to classify many different kinds of phase transition because there are so many kinds. So, a person called Ehrenfest is actually Paul Ehrenfest tried to classify different types of phase transitions based on thermodynamic properties of transition. Okay? So, his classification looks like this. He divided all different kinds of phase transition pretty much into two different kinds. First order phase transition and second order phase transition. Let's just look at the definition of each transition. First order phase transition has a certain property at which first derivative of chemical potential with respect to temperature is discontinuous. Okay? If you recall, derivative of chemical potential, for example, derivative of chemical potential as a function of temperature corresponds to entropy, right? Okay? And entropy is same as enthalpy divided by temperature, right? Okay? And chemical potential, the derivative of chemical potential as a function of pressure is volume, right? So according to Ehrenfest's classification of phase transitions, first order phase transition has discontinuous value for the first derivative of chemical potential. For example, for first order chemical phase transition, volume was the first derivative of chemical potential, has discontinuous value, right? As a function of temperature, it increases, and at the phase transition temperature, it jumps and shows discontinuous behavior. Similarly, for enthalpy, entropy, all has discontinuous behavior at this phase transition temperature. Okay? Right? For heat capacity, when first order phase transition occurs, heat capacity has infinite number at phase transition temperature. You might recall when we dealt with heat capacity in chapter 2, when phase transition, especially physical transformation, such as melting, vaporization occur, heat capacity had infinite value, right? The reason why is that the definition of heat capacity is the amount of heat to increase the temperature by 1 Kelvin, right? But when you encounter phase transition, although you add a lot of heat, there is no temperature change, right? When water vaporizes, when water boils, it occurs at 100 degrees C. No temperature rise. So that's why heat capacity has infinite number. Okay? So, most of phase transition that we know, melting, fusion, freezing, vaporization, sublimation, all of them are first order phase transition. Okay? They have these kind of characteristics. Volume, enthalpy, or entropy have this discontinuous increase, right? At transition temperature. Okay? On the other hand, there are other types of phase transition. One of them is called second order phase transition. Okay. So second order phase transition have characteristics of first derivative of chemical potential is continuous, but second derivative is discontinuous. Interesting, right? For first order phase transition, first derivative was discontinuous, but for second order phase transition, first derivative is continuous, but second derivative is discontinuous. So for second order phase transition, they have this kind of behavior. Volume enthalpy or entropy has continuous increase, right? Interestingly, heat capacity has interesting shape, right? It increases and it just stops, and it follows like this. Okay? And these two, first order and second order, are not the only phase transition. There are other types too. For example, just an example. There is a transition called lambda transition. Lambda transition is a phase transition that is not first order, but has infinite heat capacity at the transition. First order transition had infinite heat capacity, right? But lambda transition is not first order, but has infinite heat capacity, right? Such as, for example, such as order disorder transition in alloys, ferromagnetic materials, etc. Okay. For example, order disorder transition in beta brass, copper, zinc, has a lambda transition. Okay. For example, at a certain temperature, this material, this alloy, have order disorder transition. At low temperature, they are ordered like this. So copper, zinc, something like that. Very ordered arrangement. Okay. As temperature increases, each of its atom move. Okay. And islands of disorder appear. Right. Copper, they just combine together, zinc combine together, etc. Okay? And as this transition occur cooperatively. Okay? Once two different atoms changes their position with each other, it's much easier for them to exchange their locations. So as transition occur, it's very easy to change from ordered to disordered state without giving more energy. Okay? So ion grow and merge at the transition temperature where heat capacity increases and drives the transition. Okay? So they have infinite heat capacity at this ordered disordered transition. Examples of second order phase transition in solid. Just an example is change of symmetry of a crystal structure in a solid. It's just an example. There are many different types of second order phase transition, but this is one example. So, for example, we have crystal structure of tetragonal phase. Okay. And let's say that as we increase the temperature, on this direction, the horizontal direction, the crystal moves fast, okay? And on the other hand, to the vertical direction, it moves slowly, okay? To outside. And at a certain point, at a certain temperature, they would have same, like totally symmetric phase, right? As cubic phase, right? Since this direction, they move faster than this direction, right? So they would have totally symmetric phase, and after that temperature, they would move, just the crystal. would have same rate of change, right? So this kind of transition is an example of second order phase transition. Alright, so this is the end of chapter 4. Let's move to the chapter 5.